Hello students, in our last class we have started a new chapter which is chemical kinetics, and in that chapter we have discussed already the basic concepts, mainly what is the rate of a reaction, what is the rate constant of a reaction, what is the rate equation, what we mean by the order, what we mean by the molecularity, what is the differences in between the order and the molecularity. In our class, means in our today's class, mainly I will discuss about the reactions with different order, like zero order reaction, first order reaction, second order reaction, and their rate equation, along with their half-life and the examples of these reactions. So before we start with the zero-order reaction, first of all I want to discuss about the pseudo-order reaction. Okay, what is the pseudo-order reaction? A reaction in which one of the reactant is present in a large excess, shows the experimental order which is not the actual one is referred to as a pseudo-order reaction. Suppose मेरे पास कोई एक रिएक्शन हो रहा है, जिस रिएक्शन में रिएक्टेंट जो है, सपोज 2 या 3 रिएक्टेंट है और उसके अंदर कोई एक रिएक्टेंट का अमाउंट वेरी लार्ज एक्सेस में. For example, suppose when we are discussing about the hydrolysis of glucose or fructose in acidic medium, in that case we are giving water in excess amount. Okay. So one of the reactant is present in the reaction in large excess, shows the experimental order which is not the actual one. Okay. So for this type of the reaction, the experimental order, suppose we are thinking about that maybe this reaction with first order, second order or third order, but when you check after the experiment, you can see that no, the order is not like that. You can check when you are thinking that it should be second order, but after the experiment you can see that no, this is first order reaction. So this type of reaction in which the experimental order and the calculated order is different from each other, mainly this type of the reactions is known as the pseudo-order reaction. Okay, so one of the most important point in case of the pseudo-order reaction, that is the one of the reactant in this type of the reaction which is present in the reactant side in a large excess. Okay, so that point you have to remember. So just now after that the pseudo-order reaction in I am just discussing about the hydrolysis. You can check that is our hydrolysis reaction, that is the hydrolysis of the sucrose. Sucrose, everybody we know that is the cane sugar. So C12H22O11, that is the sucrose, in presence of butter, that should be in excess amount. In presence of H plus means you can make HCl or H2O. So the sucrose hydrolysis, that should be in the acidic medium in presence of the large amount of water. It will give glucose and fructose. Okay, so it will give glucose and fructose, and everybody we know that the formula of these two are same. So that is the C6H12O6. In case of the glucose, the CHO group is present, means aldehyde group is present, but in case of the fructose, the ketonic means the CO group is present. I think these things we have discussed in our carbohydrate portion, in the organic portion. Okay. So when we are talking about the acidic hydrolysis of the sucrose, in that point we are adding the water in excess amount, and we just think that no, it maybe the reaction is obviously of second order. Okay, because the sucrose is there, water is there, and the H plus is very small amount. So you can think that it may be second or third order reaction. But when you will do the experiment of the sucrose hydrolysis in presence of the acidic medium, you can observe that the reaction is first order reaction. Okay, so that's why this type of reaction is known as the pseudo-order reaction, specifically for the hydrolysis of the sucrose. The reaction is pseudo first order reaction. So here water is taken in excess amount, so the rate is equal to the rate constant into the concentration of the sucrose into the concentration of the water. Okay, because everybody we know when we are writing the rate equation, we can write that the rate of the reaction that is proportional to the concentration of the reactant. That means the rate of the chemical reaction that should be equal to the rate constant into concentration of the reactant. So the rate constant, that is K, and here the reactants are sucrose and water, and H plus that is in catalytic amount, so we can neglect it. So the water is in excess amount, so we can write the rate equation in this way, that rate is equal to K dash, means there is another rate constant which actually involves, that is K into water, into the concentration of the C12H22. This is an example of the pseudo first order reaction. So I will discuss about the first order reaction, then you can see what is the expression of the first order reaction, how can we calculate the rate constant for the first order reaction. You can easily calculate it. But what is the pseudo reaction? In case of the pseudo reaction, the reactant, one of the reactant should be in excess amount, and when we think about that, the reaction should be second or third order reaction. But after the experiment, you will see that no, the order is different from the calculated order. Okay, so this is the pseudo order reaction. So now I will start the zero order reaction, and then first order reaction, and then second order reaction. So first of all, the zero order reaction. In a zero order reaction, the rate is independent of the concentration of the reactants. ओके, तो जीरो ऑर्डर रिएक्शन का एक स्पेसिफिकली बहुत इंपॉर्टेंट पॉइंट क्या है, इसका जो रेट होगा, रिएक्शन का जो रेट होगा, जो हम लोग लिखते हैं the rate is proportional to the concentration of the reactant, तो जीरो रिएक्शन का जो रेट होगा that is independent of the concentration of the reactant. मतलब मैं कितना रिएक्टेंट दिया हूँ उसका कंसंट्रेशन क्या है, वो 1 मोलर है, 2 मोलर है, 5 मोलर, उससे कोई भी मतलब नहीं. ठीक है, तो जीरो ऑर्डर रिएक्शन में क्या होगा, जीरो ऑर्डर रिएक्शन का जो रेट होगा that should be independent of the concentration of the reactants. 1 मोलर रिएक्टेंट के लिए जो होगा, 5 मोलर रिएक्शन के लिए भी वही होगा, 10 मोलर रिएक्शन के लिए भी जीरो ऑर्डर रिएक्शन का रेट कांस्टेंट for a particular reaction same. Okay. So now let us consider a zero order reaction. Suppose we have a zero order reaction, that is A, that is a reactant, capital A, उससे क्या होगा, that is a product for product. So A arrow product. At the initial time, suppose the concentration of the reactant, that is small a. Okay. Suppose the concentration of the reactant at the initial time, that means T is equal to 0, that is A, that is small a, mole per liter. So obviously on that time there should be no product, because when we are starting the reaction on that time we can see only the reactants, there should be no product. But after, suppose time T, when the reaction is in equilibrium position, then suppose the amount of the product, that is X mole per liter. So obviously the concentration of the product, that is X mole per liter. So obviously on that point, at that equilibrium time, we can say that the amount of the reactant, that is A minus X mole per liter. Okay. So the rate of the reaction, how can we write the rate of the reaction? We can write the rate of the reaction that is dx dt is proportional to a minus x whole to the power 0. Okay, so the rate, what is the rate actually? We know that the unit of the rate we are writing, that is the concentration divided by the time. Okay, means mole liter inverse second inverse. So that means when we will write the rate of the reaction, that means the dx dt, which is proportional to a minus x whole to the power 0. Okay, why 0? Because that is our zero order reaction. If I will talking about the first order reaction, on that time you have to write dx dt is proportional to a minus x whole to the power 1. If I will talking about second order reaction, on that time you have to write dx dt is proportional to a minus x whole square. Okay, so in that case the zero order is there. That's why the dx dt is proportional to a minus x whole to the power 0. So what is actually the dx dt? dx dt is the formation of the product with respect to the time. Okay, so कितना product form हो रहा है with respect to the time, that is our dx dt. So obviously it should be proportional to the concentration of the reactant remain in the reaction. That's why we can write that dx dt is proportional to a minus x. And here in that case we are mainly talking about the zero order reaction. So a minus x whole to the power 0. Okay. So now we can write that is dx dt that equal to k into a minus x whole to the power 0, where k is the proportionality constant, or we can say that is our rate constant. Okay. So dx dt that equal to k into a minus x whole to the power 0, where k is the rate constant. Now everybody know that a minus x whole to the power 0, that is 1. So we can write that dx dt is equal to k. So ultimately, if we will integrate the dx dt is equal to k, so we can get the integration dx is equal to k into integration of dt. So that means we get x is equal to kt plus c. Okay, so here c should be 0, so we can write that after integration that x is equal to kt, so k is equal to x by t. That means the rate constant for a zero order reaction that equal to x by t. That means the concentration of the product at the equilibrium time divided by the time t. So that is our value of the rate constant. So what would be the unit of the rate constant in case of the zero order reaction? In case of the zero order reaction, the unit of k that is equal to mole liter inverse time inverse, because the concentration of the x that should be in mole liter inverse divided by the t is there. So that's why you can write time inverse. So the unit of k, that is mole liter inverse time inverse. So in case of the zero order reaction, everybody we can see that the rate is independent of the concentration of the reactants. That's why we can write that dx dt is proportional to a minus x whole to the power 0, which is actually 1. Okay, so that's why dx dt is equal to k into a minus x whole to the power 0. So dx dt is equal to k. If I will integrate it, then we will get x is equal to kt, so k is equal to x by t. So in this way we can calculate the rate constant for the zero order reaction. So for zero order reaction, the rate constant is equal to the rate of reaction at all concentration. Again I am repeating, the rate constant, that is k, is equal to the rate of reaction at all concentration. Okay, जितना भी कंसंट्रेशन होगा उसके रेस्पेक्ट में मैं लिख सकता हूँ कि रेट कांस्टेंट इक्वल है विद द रेट ऑफ द रिएक्शन, मतलब दैट इज इंडिपेंडेंट ऑफ द कंसंट्रेशन ऑफ द रिएक्टर. ठीक है, तो यही बात मैं दोबारा बोलूँगा. Okay, now everybody we know that A minus of A minus X, that is X. So here mainly in case of the zero order reaction, when I have written that A2 प्रोडक्ट फॉर्म हो रहा है, तो यहाँ पर T इज इक्वल टू 0 में कंसंट्रेशन ऑफ A था स्मॉल a और प्रोडक्ट साइड में था 0 मोल पर लीटर. बट जब T इक्वल टू T हो गया, मतलब जब इक्विलिब्रियम टाइम हो गया, तो प्रोडक्ट का जो कंसंट्रेशन दैट इज X और A का जो कंसंट्रेशन दैट इज A माइनस X. तो इसको ही मैं इन्वॉल्व किया हूँ यहाँ पर. तो A माइनस X अगर मैं लिखूँ, सो दैट इज इक्वल टू X. सो हियर A इज इक्वल टू concentration of A at time 0. That's why I have written the concentration of A at time 0, that is our A naught. Okay, so that is our A naught. And then the A minus X, what is the A minus X? That is the concentration of A at time t. So I have written A suffix t. So okay, so that is equal to X. So for zero order reaction, everybody we know that the X is equal to KT. So we can write that A T is equal to minus KT plus A0. Okay, so that is our another reaction. Now if I will plot this the graph, that is AT versus T. So from with the help of this equation, that is AT is equal to minus KT plus A0, if I will take the equation number 2, then we can see that there should be a straight line. There should be a straight line, and the slope of this straight line, that is minus A. So in case of the zero order reaction, if I will draw the graph of AT versus T, then we will get a straight line with negative slope and the value of the intercept, that is A0. Okay, so because there is the equation is y equal to mx plus c in case of the straight line. So with if I will compare that y is equal to mx plus c and here the equation number 2, then we can get this type of the graph. So comparing this equation with that of a straight line y equal to mx plus c, and AT against T graph can be plotted to get a straight line with a slope minus k and intercept of A0. Next, what is the value of the half-life of the zero order reaction? What is the half-life? First of all, we have to know हाफ लाइफ का मतलब क्या है. हाफ लाइफ का मतलब ये है, सपोज ये जो मैं लिख रहा हूँ, ये जो मेरा जो मेरा रिएक्शन था, ए से मेरा प्रोडक्ट फॉर्म हो रहा है, ये है ना. तो यहाँ पर क्या था, t इक्वल टू 0 में ए यहाँ पर हो गया और यहाँ पर 0 हो गया. अभी हम लोग t इक्वल टू टी हाफ लिखेंगे. टी हाफ का मतलब हो जाता है हाफ लाइफ, एंड ऑन दैट पॉइंट वी कैन राइट दैट AT is equal to A0 by 2. मतलब उस t टाइम में A का कंसंट्रेशन जब उसका इनिशियल कंसंट्रेशन का हाफ हो जाता है, उस टाइम को ही हम लोग हाफ लाइफ बोलते हैं. ठीक है, मतलब जिस टाइम में रिएक्टेंट का कंसंट्रेशन उसका इनिशियल कंसंट्रेशन का हाफ हो जाता है, उस पर्टिकुलर टाइम को, उस पर्टिकुलर रिएक्शन का, उस पर्टिकुलर ऑर्डर का हम लोग हाफ लाइफ बोलते हैं. तो हाफ लाइफ ऑफ जीरो रिएक्शन क्या होगा, मतलब t इज इक्वल टू टी हाफ लिखेंगे, एंड ऑन दैट पॉइंट AT इज इक्वल टू 0/2. सो फ्रॉम इक्वेशन नंबर 2, इफ आई विल पुट द वैल्यू, क्योंकि यहाँ पर मेरे पास है दैट इज AT इज इक्वल टू माइनस KT प्लस A0. So if I will put the value of AT, then we will get A0/2 is equal to minus KT half plus A0. On that point we can write that A0/2 is equal to KT half. So T half is equal to 1/2K into A0. So that is the value of the T half. So half-life is dependent on the rate constant K and the reactant's initial concentration, that is A0. Okay. So in case of the fast order reaction, we had mainly seen that the rate of the reaction that is independent of the initial concentration of the reactant, but the half-life, which is dependent on the rate constant and the reactant's initial concentration is. ठीक है, तो इस तरह से हम लोग कोई भी ऑर्डर का, मेनली हम लोग यहाँ पर जीरो ऑर्डर दिखा है, तो जीरो ऑर्डर रिएक्शन का मेनली हम लोग क्या दिखा है कि इसका रेट एक्सप्रेशन और उसके साथ साथ इसका हाफ लाइफ कैसे होगा। नेक्स्ट इसका कुछ एग्जाम्पल दिखाते हैं। इसका एग्जाम्पल है द रिएक्शन ऑफ H2 and Cl2 अंडर फोटोकेमिकल कंडीशन. So H2 plus Cl2, if I will put the H ring, that means the sunlight, that's why I have written the photochemical condition, we will get to HCl gas. So that is the example of the zero order reaction. Okay, so if I will think that, okay, here H2 is 1, Cl2 is 1, so that should be second order reaction. So that is our calculated one. Okay, calculated order. But if I will do the experiment, and on that point we can see that no, the order is 0. That means the rate of the reaction is independent of the concentration of the hydrogen gas and the chlorine gas. Okay, so that is the example. Another example, there is the decomposition of the nitrous oxide over a hot platinum surface. Decomposition of the nitrous oxide means N2O over a hot platinum surface, that means platinum hot, and it will give 2N2 plus O2. So there is the decomposition of nitrous oxide over a hot platinum surface. There is also the example of the zero order reaction. Next is the iodization of acetone, means in H plus ion rich medium. So acetone, everybody know that this is CH2COCH, it is our acetone, and if I will add I2 in presence of H plus, then we will get ICH2COCH3, that is iodoacetone plus HI. So that is also the example of the zero order reaction. Next I will start with the first order reaction. So in case of the first order reaction, the initial thing is same, but the reactant, that is A, the product, that is our PDT, I have written here the same thing, at initial time A0, at T is equal to T, A minus XX. So that is similar to the zero order reaction. For a first order reaction, the rate of the reaction, that is dx dt, is directly proportional to the concentration of the reactant. Obviously, तो यहाँ पर जो रेट एक्सप्रेशन होगा जब जीरो ओवर का, तब हम लोग लिख रहे थे dx dt is equal to k into a minus x whole to the power 0. बट यहाँ पर फर्स्ट ऑर्डर है, इसलिए हम लोग लिखेंगे dx dt is equal to k into x a minus x whole to the power 0 के जगह पर मुझे ये जो पोर्शन है जहाँ पर मेरे एरो तुम लोग देख रहे हो, यहाँ पर मुझे 1 लिखना है, तो 1 लिखना ना लिखना बात बराबर, इसीलिए मैं ऐसे लिखा हूँ. तो इसको मैं लिख सकता हूँ, दैट इज dx by a minus x is equal to k dt. ये जब आ गया तो इसको इंटीग्रेट करो. इंटीग्रेट करने के बाद हम लोग को मिलेगा इंटीग्रेशन ऑफ dx by a minus x is equal to k into integration of dt. That means dx by a minus x, that is equal to minus ln a minus x. So that is equal to kt plus c. The integral constant can be calculated by putting the t is equal to 0 and x is equal to 0. तो इनिशियल जो मतलब यहाँ पर जो इंटीग्रल कांस्टेंट आया है, जो यहाँ पर c आया है, इसको भी हम लोग को निकालना है. इसके लिए हम लोग क्या कर रहे हैं, एट टाइम 0 t is equal to 0 क्या हो रहा है, x का वैल्यू कितना है, x का वैल्यू 0 है, तो t is equal to 0 जब x is equal to 0 पुट करेंगे तो we will get c is equal to minus ln a. तो c is equal to minus ln a आ गया. तो ये जो एक्सप्रेशन है, इस एक्सप्रेशन में अभी c is equal to minus ln a को पुट कर दो, तो क्या आएगा, minus ln a minus x is equal to kt minus ln a. That means ultimately we will get k is equal to 1 by t ln a by a minus x. तो ln, everybody we know that ln का मतलब क्या है, ln का मतलब है 2.303 log, that is the meaning of the ln. तो हम लोग लिख सकते हैं k is equal to 2.303 by t log a by a minus x. So that is very important rate expression for the first order reaction. You can see that so many mathematical numerical problems are coming in the exam, that you have to calculate the rate constant for the first order reaction. Yeah, you have to calculate the time taking for the completion of the reaction, which is actually completed 80%, 90%. So like there's so many things will come in your exam. So k is equal to 2.303 by t log a by a minus x. So what is the unit of k? So unit of k, everybody know that there is no unit because the log is there. So log a by a minus x, there is no unit. So only the unit which comes due to the presence of the 1 by t. Okay, so the unit is time inverse only. So that is minute inverse or second inverse. So that is a very important rate expression, that is k is equal to 2.303 by t log of a by a minus x. Now the value of k can be found by substituting the values of A and A minus X determined experimentally at time interval T during the course of the reaction. So we can write that K is equal to 2.303 by T2 minus T1, and here log of A minus X1 by A minus X2, where X1 and X2 are the amounts decomposed at time intervals T1 and T2 respectively from the start. Now if I will want to plot the graph of ln A by A minus X versus T, so obviously it will give a straight line, and the straight line actually passing through the origin is because the slope is only K. So the value of K for a first order reaction is independent on the concentration of the reactants. So obviously in that case, in the particular first order reaction, the value of the rate constant is independent on the concentration of the reactants. So if I will plot the ln A by A minus X versus T, then on that point we will get a straight line with slope K. Okay. Now what is the half-life of the first order reaction? We again I am saying that T is equal to T half when the X is equal to A by 2. So K is equal to 1 by T half ln A by A minus A by 2, because we had seen that the rate expression for first order reaction, that is K is equal to 1 by T ln A by A minus X. So here I am putting the value of X, that is A by 2, and in the case of T we are writing T half. So T half is equal to 0.693 by K. That is also very important because that is the half-life of the first order reaction, that is 0.693 by K. So the half-life of the first order reaction is a constant and independent of initial concentration of the reactant. So half-life क्या है, half-life हम लोग देखते हैं, इसका वैल्यू 0.693 by K है. तो फर्स्ट order reaction का जो half-life है ये एक्चुअली कांस्टेंट है और ये इनिशियल कंसंट्रेशन ऑफ द रिएक्टेंट के ऊपर डिपेंड नहीं करते, क्योंकि यहाँ पर हम लोग देख रहे हैं कि टी हाफ का वैल्यू में ए या ए माइनस एक्स कुछ भी नहीं है, ओनली के है. नाउ द एग्जांपल्स, द फर्स्ट ऑफ ऑल द एग्जांपल इज द डिकम्पोजिशन ऑफ H2O2 इन aqueous solution. If I will decompose the H2O2 in aqueous solution, that means H2O2 which will give the H2O plus half O2. So that is the example of the first reaction. And next, hydrolysis of methyl acetate in presence of the mineral acid, that is the methyl acetate, that means that is ester, that is C3COO plus water, which will give C3COO, that is the acetic acid, plus C3, that is methanol. So that is the example of the first reaction. Next, decomposition of ammonium nitrite. Okay, ammonium not nitrate, ammonium nitrite, मतलब NH4NO2 in aqueous solution. और aqueous solution में मैं ammonium nitrate, that is NH4NO2 को रख दूंगा तो it will be decomposed and it will form N2 plus 2 water. And next one is the hydrolysis of the diazoderivative. Hydrolysis of the diazoderivative, that is mainly in the organic portion, that is C6H5N2 plus Cl minus, that is our benzene diazonium fluoride plus water, which will give phenol plus nitrogen plus HCl. So that is also the example of the first order reaction. Okay. So in our today's class, mainly we have discussed about the pseudo-order reaction. What is the pseudo-order reaction? And in case of the pseudo-order reaction, we had seen that one of the reactant concentrations should be higher than the others. Next, I had talked about the zero-order reaction. We had seen that in case of the zero-order reaction, the rate of the reaction is independent of the initial concentration of the reactant. एंड उसके बाद हम लोग ग्राफ ड्रॉ करके भी देखे, वहाँ पर स्ट्रेट लाइन आ रहा था तो जिसका नेगेटिव स्लोप था. तो ऐसे हम लोग क्या वैल्यू निकाल सकते हैं कोई भी जीरो रिएक्शन के लिए. उसके बाद उसका हम लोग यूनिट भी देखे हैं, उसका हाफ लाइफ भी देखे हैं. तो हाफ लाइफ हम लोग देखे हैं तो वो रेट कांस्टेंट भी है और उसमें इनिशियल कंसंट्रेशन इन्वॉल्व है. तो इसलिए हाफ लाइफ ऑफ द जीरो रिएक्शन which is actually dependent on the rate constant of the reaction and the initial concentration of the reaction. Next, the examples of the zero reaction, and then we have discussed about the first reaction. This is very important in case of the first reaction, the rate expression, which is actually K is equal to 2.302 by T log of A by A minus X. So this is very, very important for numerical problems also. And then from that expression we had calculated the unit of the rate constant, and after that we had calculated the half-life along with a graph we got a graph with slope that is actually positive in case of the first order reaction, and finally we have discussed few examples of the first order reaction. Okay, so in our next class, mainly we will start our class with the second order reaction. Okay, thank you.